Thank you, Jose. So first, I'd like to thank the organizers for my kind invitation. So it's my first time to CERN, and I'm enjoying this visit a lot. So today, I'm going to talk about suppressing chemotactic blow-up, where we are coupling the usual Keller-Segal equation in 2D with the fluid equation. So this is the joint work with Zhongtian Hu, a graduate student at Duke University, and Alexander Kiselev, also at Duke. So I guess to this audience, I don't need to introduce what is the Keller-Segal equation, right? So this is the classical example of a collective motion of bacteria where they are attracted by a self-emitted chemical. So throughout the talk, I'm going to use rho to denote the bacteria density and C to denote the chemical concentration. Okay, and I'm only going to discuss the parabolic elliptic version of Keller-Segal. So in 2D, this audience, there are many experts that know it much better than me. It's well known that there is this critical mass phenomenon. Namely, as long as the mass satisfies that it's bigger than 8 pi, then all the solution with initially finite second moment will have a finite time blow-up, whereas as long as the mass is below this threshold, the solution will be globally bounded and it will be dissipating according to the heat equation scaling. And at exactly the critical mass, there won't be a finite time blow-up, but the solution could be concentrating towards a delta function as time goes to infinity. Okay, so throughout the talk, I'm not going to work in R2, rather I'm going to work in a bounded domain. And for a bounded domain, I just wanted to point out that there is a very similar result. So one small modification that one need to make is that, well, because the usual assumption is that, well, in this case, so the normal derivative of the chemical is equal to 0, so the equation becomes a Neumann boundary problem. And in order for that problem to have a solution, we need to subtract a constant, for example, the average density of rho for that problem to be solvable. Right, so this is only just a small modification. And in the bounded domain case, there is also a critical mass phenomena, except that the number will be 4 pi instead of 8 pi. Okay, so that is the vanilla version of the Keller-Segal equation in the plane and in the bounded domain. What my talk is about today is that, well, we are going to couple this Keller-Segal equation with an incompressible fluid and whose velocity field is given by U. Okay, so I would say the problem is more motivated by math reason rather than real biological reason, but it is indeed motivated by the fact that many chemotaxis processes often take places in fluid, and we want to understand that whether the extra coupling with this advection term by U would prevent blow-up or not. Okay, so far, I have modified the rho equation by adding the advection term, but I haven't introduced to you what U is, right? So now, in the previous literature, there are mainly 2 different classes of U. So they can be loosely grouped into passive advection and active advection. So by passive advection, what I mean is that U is given to you by the equation, okay? So it is a given velocity field that is incompressible. And in this case, so the previous equation simply becomes this, right? Here, let's say U is a given divergence-free vector field, and to be convenient, let me multiply a constant A. So A denotes the amplitude of the flow. So given any initial condition, it is known that the blow-up can be prevented by the following kind of flow. So one type of flow is the so-called mixing flow or diffusion enhancing flow. I won't be giving you the precise definition, but intuitively, these flows are really good at breaking the density apart. Okay, and then for example, for these densities, the U is very good at spreading it out. And then once U breaks it apart, you can imagine that, well, so these kind of phenomena would help the diffusion term to smooth things out. okay? So for such kind of flow, Kiselev and Xu shows that you give me any initial condition rho 0 and such kind of flow U, then I can find a sufficiently large amplitude such that the blow up doesn't happen if the advection is strong enough. Okay, so this is one type of result. Another kind of flow that is often considered is the shear flow. Okay, so this is like what the velocity field of a shear flow look like. Basically, it's just each horizontal layer is traveling at a different speed. And Bedrosian and He showed that, well, for such kind of shear flow, if the amplitude is sufficiently strong, of course, the strength here will depend on the initial condition. Okay, so you first give me an initial condition, and then they are able to find a sufficiently large amplitude such that all the sufficiently large amplitude will prevent blow up. So intuitively, the mechanism here is that if you consider this velocity, if you consider this density distribution, and you just passively advect it by U without thinking about the chemotaxis, then the shear flow will be wrapping it around the torus. And so you can see that such U will make the solution weakly, it almost become a one-dimensional density, right? And we know that 1D Kähler-Segal doesn't blow up. So roughly speaking, this is like the key idea of their proof. But both of these two results are in the spirit that you first give me an initial condition, and then I will decide how big the amplitude needs to be to prevent blow up. So what about the other round? What if you give me the flow first? Well, it turns out that Winkler shows that so if you fix the flow first, then any flow that is sufficiently smooth will not change the critical mass. So namely, for any given passive velocity field that is sufficiently smooth, then for any mass that is bigger than the critical mass, you can always make the initial data sufficiently concentrated such that the blow up can still happen. Okay, so this is the previous results when it comes to passive flow. Another class of flow that we are going to consider is the so-called active advection, which means that the velocity field U here is no longer something that is given to me by the equation, but rather we are going to consider a system where rho and U are coupled together and they both evolve in time. Okay, so for most of these work, the coupling is done by the fact that, well, so when the chemotaxis takes place in water, they assume that the density rho of the bacteria is heavier than the water density itself, right? And therefore, so in the U equation, so I think most of these work assume that the U satisfies the Navier-Stokes equation or the Stokes equation, where the U and rho equation are coupled by buoyancy, which means that a heavier density of rho would be dragging things down. Okay, so there is this coupling term in the U equation. The literature in these Kähler-Segal and fluid coupling are vast, and by no means I was able to include them in all the slides. But to the best of our knowledge, all the global existence results for Kähler-Segal with fluid coupling can roughly be grouped into these three different classes, where I am using different color code here to denote which class they belong to. So the global well-posedness is either, in all of these results, is either proved by assuming that the initial density is small, or so for example, it's a small perturbation of a constant steady state. So these blue dots include means the assumptions where the initial condition have certain smallness. And these results with the red dots means that so if you remove the fluid part, then the equation itself is still global well-posed. So for example, this can be done by imposing some flux limitation or imposing degenerate diffusion. Okay, so in that sense, it's like without fluid, there is global well-posedness, and after adding the fluid, there is still global well-posedness. So in the previous literature, the only results that we are able to find where it's really the flow that is actively preventing blow-up to happen is the last result by Zeng, Zhang, and Zi, where they show that suppose your flow is a sufficiently strong co-ed flow. So co-ed flow is this shear flow that I showed you in the previous picture. Then, so they showed that even with the active coupling, such kind of flow is still can prevent blow-up. Okay, but here the sufficiently strong is also depending on the initial condition, which means you give me an initial condition, I can find a sufficiently strong co-ed flow such that such active coupling of the two equations will be globally well-posed. Okay, so these are the previous literature regarding coupling Keller-Siegel with an actual with the active fluid, and with Sasha and Zhongtian, we want to consider a coupling that is simple enough for us to obtain some rigorous results. So this is the coupling that we studied. So first of all, the rho equation is exactly as I showed you. There is this advection term here, and for this term here, it's just the gradient C, okay, except that I have written C into the same equation, so it becomes an inverse Laplacian, and I'm using this inverse Laplace n inverse to denote that this is the inverse Laplacian when we are solving the elliptic equation with Neumann boundary condition. Okay, this is what n stands for Neumann, and because we set up the problem in a bounded domain, we need to subtract an average density rho m, which is a constant, to make sure that this elliptic equation is solvable. Right, so that is the rho equation as usual. So for our flow, instead of considering the flow that are Stokes or Navier-Stokes, we want to study with something that is as simple as possible, okay, which is the Darcy's law. So, but it's the Darcy's law for incompressible porous media. Okay, so this is what it means. In the incompressible porous media, instead of the Newton's law, the fluid will have no inertia, which means that the velocity field is directly proportional to the force. Okay, and here the force is the gravity itself. So this second term here is the force. Okay, so E2 is the vertical direction, and rho times E2 means that, well, the part with the heavier density is dragging it down more. So that is the gravity term. But meanwhile, so the fluid in the porous media, we force it to be incompressible, which means that while the force itself is just the gravity, the incompressibility will be forcing the fluid to have this extra character, and this gradient P is there to make sure that the fluid the U is incompressible. Okay, so this is like, if you are familiar with incompressible Euler equation, the P plays the same purpose here and there. So this is something that can be explicitly solvable, because if you apply the divergence U to both sides of the equation, you will have Laplace P is equal to blah, 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 and you can explicitly solve for P, plug it into the equation to write U explicitly in terms of rho. Okay, so that is the coupling that we want to study. Just to give you an intuitive idea of what this coupling look like, so suppose I have a picture of rho like this, where the intensity of the red colors denotes heavier density and not so heavy density. Then the gravity itself wants to pull this heavy red dot on the bottom, right? But as I mentioned, that this gravity field itself is not incompressible, so the actual U is, in some sense, this vector field projected into the class of incompressible vector field. So the final U that is induced by such kind of density actually looks like this. So in general, the heavier part still tries to go down, but the fluid overall is incompressible on the whole domain. Okay, so if you forget about the Keller-Segal equation and just advect the density by such Darcy's law, then intuitively after time t, there is still the effect that, well, the heavier part in general tends to go down. And this equation itself is called the incompressible porous media equation. Its local well-posedness is established by Cordoba, Gancedo, and Uribe, even though the global well-posedness is still open because it's just an advection equation without any diffusion, right? Okay, so now when this equation is coupling with the Keller-Segal equation, because there is diffusion in the Keller-Segal equation, local well-posedness of the system is actually quite standard to show, and actually one can show that the solution can be extended as long as, let's say, the L2 norm of the density doesn't blow up. Okay, so local well-posedness is easy, but of course the question is that whether rho will have a finite time blow up or not. So when we begin this project, heuristically, we were hoping to prove that blow up doesn't happen for large G, because intuitively one can think that, well, large G means that the gravity is pulling really hard, the density that are heavy. So in that sense, a large G should be very effectively making the density into these one-dimensional structure where the heavier one are on the bottom, the lighter one are on top, and because we know that 1D Keller-Segal doesn't blow up, maybe we can prove that, well, for this 2D system, it doesn't blow up for large G. Okay, so that is our starting point when we embarked on this project. But halfway during our project, we realized that, well, we can actually prove something better. Okay, this is the final result that we showed. It says that, well, for this coupled system, you give me any G, so G is the gravitational constant, that is not equal to 0. Okay, so we make it positive because it makes us feel better that gravity is pointing down, but really the sign doesn't matter. So for any G bigger than not equal to 0, we are able to show that the solution is actually globally regular in time. Okay, and this result is a bit to our surprise because when G is equal to 0, this is exactly the Keller-Segal equation where we know that the solution will blow up if the mass is bigger than a certain threshold. Right? So in that sense, the result can be interpreted as long as you have a tiny bit of this chemotaxis coupled with fluid, somehow this tiny coupling will be already sufficient to prevent a blow up to happen. Okay, so let me first very briefly outline to you the proof strategy, which we think it's somewhat not traditional. Usually when people prove that the system is globally well-posed, it is often done by tracking the a priori estimate of certain norm, right? You show that, well, this norm, its evolution can be controlled, it doesn't blow up. Somehow we are not able to do that for this system of equation. We are only able to show that there's no blow up by the following argument, which we think is a bit weird. So we are going to, in the next few slides, I'm going to introduce to you two main characters of the proof. One is our old friend, which is the L2 norm, and the other thing is the other term is specific to this Darcy's law, which is the potential energy. Okay, it's a gravitational energy. So the proof is done by, we cannot just track one of them to say that the equation is globally well-posed, but we track the evolution of both of them simultaneously. Okay, and then the key step of the proof is the following argument, where we were able to show that suppose the solution blows up in finite time, which means the L2 norm needs to blow up, and we prove that suppose this happens, then the potential energy, for some reason, it must be driven down all the way to minus infinity. Okay, and what is wrong with the potential energy going to minus infinity? Well, if we look at the definition of the potential energy, it is rho times the height x2, right? We are working with the bounded domain with the upper and lower boundary. So really x2 is something between 0 and pi. It's like a finite number. And the integral of rho has a finite mass, right? So it means that this E actually has an a priori lower bound and upper bound, which are two constant. So so it can never go to minus infinity, right? In this case, it's actually positive for all time. So in that sense, suppose there is a blow up, then near the blow up time, we would be having this unbearable heaviness of being, where I am like stealing the title of the unbearable lightness of being from the famous novel by Milan Kundera. But anyway, so by this unbearable heaviness of being, we are able to say that, well, no, you actually can blow up. Okay, so that is the argument, roughly. And now let me formally introduce to you to our two characters of the proof. Okay, so the first main portion is the control of the L2 norm. And for this part, really, this is nothing new. It is the very standard energy estimate for the Keller-Segal equation itself. And actually, for the evolution of the L2 norm, you won't even see the advection coming into play. Okay, so the reason is that if you think about the rho equation, there is the Keller-Segal part, right? And there is also the advection part. But the advection is really just shifting rho around. So for this reason, it's not going to contribute to the evolution of L2 norm or in general any LP norm. So by a divergence theorem, the advection is immediately canceled out, and the evolution of the L2 norm is really the same as the Keller-Segal equation itself. Okay, oh sorry, this should be not equal, this should be less than or equal. So if you do the evolution of the L2 norm squared for Keller-Segal, you will see that, well, there is the diffusion term dragging it down, and meanwhile there will be the integral of rho cube term. But if you really want to write that term in terms of the L2 norm, then you do the Gagliardo-Nirenberg, and then you will see that the L2 norm's fourth power will pop out. Okay, so this is the very naive energy estimate, but at least this naive energy estimate tells us something, that you can't grow to, so your L2 norm can grow, but it cannot grow too fast, right? In the sense that if you look at this, if you call the L2 norm squared by y, then this is the ODE that says y prime is less than or equal to y squared. So in order for this L2 norm squared to go from 2 to the power n to become doubled, you need to wait at least 2 to the minus n time, right? It can't happen immediately. So that is a simple fact, but it will be useful. And another thing that we want to look at from the L2 side is that, well, so we want to look at which guy is the term that is causing the blow up. Suppose there is one that happens. Okay, so we decompose the energy, we decompose the density into the horizontal average, where rho bar is a constant on each horizontal layer, and everything else that is put into this rho tilde term. Okay, so rho bar is only a function of x2, and if we do the Gagliardo-Nirenberg inequality, we see that, well, the gradient rho bar L2 squared can actually kill the L2 norm of rho bar 6th power, but for rho tilde, it is exactly the 4th power. So in that sense, these two terms have the balanced power for the rho tilde term. Right, and actually the powers are balanced. This is exactly why there is a critical mass phenomena, where for small mass you can't blow up, but for bigger mass you can. Right, so for this simple inequality, we can identify that, well, the rho consists of these two parts, the horizontal average part and the rest, which is rho tilde. And between these two terms, if there is a blow up, the culprit term has been rho tilde. So we can really just remove rho bar from the picture and just make its contribution into here. But if there is a blow up, then sorry, again, this should be a differential inequality instead of equality. So the rho tilde is the one that is causing the blow up. Okay, so far, nothing new. This is the completely standard energy estimate. And now let me introduce to you the second character of our proof, which is the potential energy. So this is the definition of the potential energy, which is motivated by the fact that the equation is driven by gravity, right? And now let's look at how the potential energy is evolved in time. Because the equation for rho will have three terms. That is the advection, the diffusion, and aggregation. And it is not surprising that you will be seeing exactly these three terms on the evolution of the potential term. right? So for now, let me highlight to you the contribution that is caused by the advection term. Of course, there are other contributions that is made by diffusion and Keller-Segal, but let me intentionally hide these two terms for you for now. Okay, so suppose we only have the advection term, then it turns out that this term's contribution has a sign. So this is not surprising, because if you think about what advection term is caused, it is caused by the gravitational force that is projected to the divergence-free vector field, right? And because the gravity is pointing down, it's not surprising that this term gives a negative contribution. And it can be explicitly computed that the advection term gives this exact negative contribution, where, so if you count the order of this term, then there is one partial derivative, but meanwhile, it's not the L2 norm, it is the h-1 norm of it. Okay, so it means it makes this term like the L2 norm in terms of order, but it is the weighted version. Right? If we are looking at it into the Fourier side, then so it is like the L2 norm, but with this multiplier that is K1 over the modulus of K. So in this Fourier frequency plane, where the frequencies are living on the integer dots because the domain is like a square, so I am using the different intensity of colors. So when K1 is proportional to the absolute value of K, the weight is like order 1. But if the modes, for the modes that are almost living on the vertical line, this weight is equal to 0. Right? So one simple observation is that, well, this term is bounded above by the L2 norm of rho squared, and actually even L2 norm of rho tilde squared. Rho tilde is like all the modes except the middle one, right? But then the question is that, okay, so this is just a one-side inequality, and we want to know that whether this thing is comparable to rho tilde squared, or can it be much smaller? Right? Of course, this depends on where these modes are living, right? They will be much smaller if the modes are very concentrated near the K2 axis, but they will be comparable to each other if the modes are more evenly spread out. Okay, so far this is, I have been discussing these two things, the evolution of L2 norm and the evolution of the potential energy separately. And now it is the exciting moment that they finally meet each other. So the two main characters, this L2 norm and this h-1 norm squared, these, that appears in the evolution of the potential energy, the two characters are linked by the following key lemma. Okay, so let me introduce to you backwards what this key lemma means. So this line here is simply our favorite Nash inequality, or like special version of Gagliardo-Nirenberg in 2D. Right? However, without the assumption here, we know that, well, this is exactly the right power for the Nash inequality, and I won't be able to put a constant that is sufficiently small. Right? Because for the Nash inequality on the bounded domain, this constant is like, there is a sharp fixed constant that is depending on the shape of the domain. Right? And if I replace that constant by anything smaller than that sharp constant, then this inequality would be wrong, right? But now we want to ask ourselves that, well, what if we really want to improve the constant of this Nash inequality to make it sufficiently small? And the answer is that, well, for general rho tilde, of course you can't do it, right? There is this sharp constant, it can be improved. But if we are assuming that this rho bar is almost a horizontally stratified density, then we can actually improve this constant to be something as small as we want. Okay, so this is where this assumption comes into play. It says that, well, assume that this So this term here is much, so notice that these two norms are of the same order, right? So this is exactly the term that appears here, which is like the weighted L2 norm, except that it is, the weight is equal to 0 around the K2 axis. So the lemma shows that, well, suppose this weighted version of L2 norm is much smaller than the L2 norm itself, then what it tells us is that, well, the contribution of this weighted L2 norm, so most of the modes in the L2 norm should be living near the K2 axis, right? And then in this case, if we know that information, we would be able to improve the Nash inequality. So it can be seen as somewhat an anisotropic Nash inequality, where we can improve the constant to be as small as we want by this extra assumption. Okay, so I'm not going to discuss the proof of the lemma. It's just by looking at the Fourier series, it turns out it's not too difficult. Okay, but how will this lemma help us with the proof? Well, here is the idea. Let me first give you a sloppy version of proof, and later I'm going to introduce how to make it more rigorous, okay? So in the sloppy version, I'm going to assume that, so to rule out a blow-up, I'm going to assume that the L2 norm of rho just straightly monotone increase all the way to infinity to the blow-up time, okay? I'm going to first show that why this is impossible. Well, suppose somehow the L2 norm just all the way monotone increase to infinity, then we first look at this simple L2 norm estimate to ask ourselves that, well, what needs to be true in order for it to always increase? Right? So that is the differential inequality. So we see that, well, in order for the L2 norm, or we can look at the Rotilde version. So in order for the L2 norm to all the way blow up, we need the L2 norm fourth power to be beating this diffusion term here. Right? So which means that if blow up really happens, then we know that for all the time approaching blow up, this Nash, the opposite direction of the Nash inequality hold, where with this constant not being so small, right? That is how we can drive the L2 norm to blow up all the time. And then if this is the case, then we compare it with our lemma. The lemma says that, well, if this assumption is true, then the constant in the Nash inequality can be made arbitrarily small. But here it says that it is not arbitrarily small, so it means that this assumption can't hold, right? So the assumption can't hold means that this weighted L2 norm is not too small compared to the L2 norm itself, right? Okay, so now we look at what happens as the L2 norm squared doubles. As the L2 norm squared increases from 2 to the power n to 2 to the power n minus 1, first of all, the naive L2 energy estimate says that, well, this can't happen immediately, right? You need to wait at least time 2 to the minus n for it to happen. And also, we track that over this time, how much potential energy has dropped, right? So in the three terms of the potential energy, I was cheating. I was asking you to not look at these two terms first, right? If we ignore it, then it's just the advection term strings multiplied by the time, right? So the advection term exactly causes the contribution, that is this weighted L2 norm, because we concluded that the weighted L2 norm is comparable to the L2 norm, so its magnitude is comparable to 2 to the power n, right? And the size is 2 to the power n, the time is at least 2 to the minus n, so it means the amount of drop of the potential energy over this time period is like the product of them, which is of order 1. Right? So basically this argument, this very hand-waving argument says that suppose we have a finite time blow-up where the L2 norm monotone increases, then every time the L2 norm squared doubles, we need to pay a price. The price is that the potential energy is dropping by order 1, right? But the potential energy is not something that you can drop to arbitrarily negative, right? Because it's a bounded domain, the potential energy is non-negative. So you only have a finite budget to drop, right? Which means that you can't be doubling your L2 norm infinitely. You can at most double a finite number of times. So this is where the contradiction happens. So this is roughly, I would say, the key spirit of the proof. Of course, you must have noticed that, well, there are several places that I have been sloppy in the proof. The first is that, well, so I have been assuming that the L2 norm just straightly monotone going to infinity, right? But you may ask that, well, but what if this is not the case? What if the L2 norm goes up and down before it blows up? And also, in the contribution of the time derivative of the potential energy, there are three terms. There are the contribution from advection, diffusion, and aggregation, right? So far, I have been only using the contribution of the advection term, but what about the rest of the term that I tell you to ignore at this moment? Right. So we need in the actual proof becomes a lot more technical. But these are, I would say, eventually it's doable. So for example, in order to fix the first issue, what if the L2 norm is increasing to it's blowing up in a non-monotone way? This can be fixed by introducing the good and bad time interval. Okay, so namely, we pick a base interval that is sufficiently large, and then we mark this level set of 2 to the power n, okay, for each n. And then we track suppose there is a finite time blow up happening, how is the L2 norm growing to infinity? And then, so over this evolution, we track several the important time, the times, such that the first time that it hits, let's say 2 to the power n0, we mark this is like the initial time that we are going to care about the evolution. And after that, every time that your L2 norm squared either hit the one level below or it hits one level above, we mark this time. Okay, so this is going to give us an infinite sequence of time where between each of these two times, your at the end, the endpoint of the L2 norm squared either dropped by a half or increased by 2. Okay, and then because we assume that it blows up. So if at the end point you ended up your L2 norm squared gets doubled, we call it a good time interval. And if your L2 norm gets a half, we call it a bad time interval for the blow up. Okay, and also we label, so like what is the level of these intervals? Okay, by looking at the value, by looking at like the interval that they are, so by looking at what interval is the L2 norm squared. And to make the proof rigorous, we need to track the evolution of the potential energy on every good interval and also on a bad interval. So on a good interval, by looking at pretty much it's the previous proof, except that we need to make the proof to be a time integral version. And also we need to, for the terms that I have been telling you to ignore, we actually have to look at them and to show that, well, they are not too harmful. They don't affect the big picture. And we show that on every good interval of level n, the potential energy, we won't be able to show it decrease by order 1, but we can still show that it decreases by at least order n to the minus 1. Okay, and then also, what about on the bad interval? So in this case, so there are effects coming from the diffusion term and the aggregation term. So we won't be able to show that the potential energy drops on the bad interval. It could increase a little bit, but we show that, well, it can't increase too much. It can increase at most by 2 to the minus n over 3. Okay, which is actually much smaller as compared to this for a large n. And also, so the energy may be going up and down, but if we only track the things that are happening at the level n, one can easily check that overall the number of so the good interval and bad interval must be interlacing, and the number of good intervals will be exceeding the bad interval by 1. And therefore, if we are summing up the evolution of the potential energy over each of these intervals, then we see that, well, suppose there is the blow up, then the good intervals will be driving the potential energy to drop by this sum of the harmonic series. But because this diverges, we still get the potential energy will go to minus infinity, which we cannot afford. Okay, so that is the final idea of the proof. So we have done this very simple coupling in a bounded domain, but there are still some open questions. So for example, in the full domain case, our argument is able to rule out, so it says that, well, you can't blow up in some point in the interior of the domain. However, we don't know whether it is possible that at the time of the blow up, the density also goes down to minus infinity. Okay, so in this case, if the L2 norm blow up while the potential energy really become minus infinity, we think it's unlikely, but we are not able to get a contradiction at this moment. And also, we deal with the easy case, the parabolic elliptic Keller-Segal equation. So what about we change it to parabolic, or for the coupling, we are currently coupling the Keller-Segal with Darcy's law. What if we couple it with the Stokes or Navier-Stokes equation that are more commonly used in the literature? Okay, and even for the simple equation, the simple system that we considered here, so we showed that there is no finite time blow up. Actually, we are able to get some global in time L infinity bound if we are tracking the constant really carefully. But a global in time bound doesn't mean the long time behavior is clear. Right? And usually the long time behavior is done by some Lyapunov functional, but here we don't think there is a Lyapunov functional for this system. So even though we know that the solution won't blow up, we still don't know whether it will be converging to some steady state or it can have some other type of behavior. But overall, so the key idea of this proof is that, well, by certain active coupling for Keller-Segal and the incompressible system, so we give the first proof that, well, a sufficiently small coupling constant can suppress blow up in some cases. And probably that's why the authors in Singapore, they choose to like clump to each other on the land, not in the water, because they know that they can't blow up in the water. Thank you for your attention.
Okay, questions, comments?
Marcel?
Hi, thank you very much for the very nice talk. My question is maybe about the last parabolic chemotaxis equation, because if I understand well, in your case, chemotaxis field is not transported by the fluid,
yeah.
Which is because you assume it's quasi-stationary, so it diffuses so fast that it equilibrates. But I suspect in the parabolic case, there should be also advection on the chemical.
Yeah, I agree with you. Right. So if we make it into the parabolic system, then not only rho should be transported by C, but also by U, but also C should be also transported by U.
Okay.
Yeah, we haven't looked into that case yet.
And so my side question, so I'm terribly bad in the fluid, but would it make sense to have an equation which is stationary on C, as you did there, but transported in should it make sense that the advection fluid is also on the chemotaxis, even at with a sort of quasi-equilibrium?
You mean for even the parabolic elliptic case?
Yes.
Yeah, that's a good point.
I don't know if it even makes sense to have a U grad C minus Laplacian C equals to rho something.
Yeah, so I think it depends on the modeling assumption, right? Yeah. Like what is the nature of this chemical C? But okay. I agree that I think it also makes sense to have this like elliptic version where C is transported by U. In that case, I think it makes sense to also study the same problem. There is one term that we can't control, so we don't know the answer.
Any more questions?
Thank you for the nice talk, and also thank you for the effort in explaining the details in the proof. I just have a technical question. In your anisotropic Nash inequality, can you show me the slide again? Yeah, of course, this is just a sketch of the proof, but the first item, you say that one needs this, but roughly speaking, how do you make sure that the gradient also, the gradient term on the right-hand side doesn't grow with the same speed, and so you don't have this inequality maybe? I mean, you're saying because the L2 norm increases, so you have this inequality. How comes the gradient doesn't grow faster in L2?
So are you talking about like the later part or the...
No, I'm talking about the first item in your list.
The lemma itself, right?
No, in your argument, when you say in order for the L2 norm to increase, one needs this inequality.
Right,
How do you conclude that? I mean, can it be that the gradient of rho tilde in L2 also blows up and grows faster than...
yeah, but it's about the comparison between the two, right?
Okay.
So if we look at, so this is like this should be a differential inequality, right? And then suppose the right-hand side is negative. Let's ignore this constant, right? You need this term to beat that term, right?
Thank you very much for the very interesting explanation. On the very last technical part, you said there is this. In the slide before, can I easily catch the intuition why on a bad interval the energy increases by such a small amount only?
So the reason is, I would say, I don't see any intuitive way to explain it, but we really need to look at so the energy evolution. The potential energies evolution is given by these three terms, right? So the advection term can only drop it down, which means all the effect that makes it increase has to happen from these two terms. Right, and then intuitively, so in the estimate, we are heavily relying on the fact that, well, not only we need to control these two terms, but we also need to take into effect that it is a bad interval, which means that we already know that this term itself, we are under the assumption that the L2 norm doesn't grow. So it's the reverse inequality here that holds. So we are using that fact to control the evolution of the potential energy.
Any more questions? I have one comment, and it's related to Vincent also a little bit. Probably it's a good idea to come back to the origin of many of these questions that probably Marco Di Francesco remembers. There is a famous paper of Goldstein about oxide axis, in which the origin of the coupling, instead of being a chemical, is just oxygen on a droplet. And then in the experiment, they see that they have rollings and oscillations. It would be nice, and there are models written for that, it would be nice to see if these ideas could be useful to prove that kind of oscillations they see, because there is no explanation of that oscillation from the PDE point of view. And I think that was the motivation of the first paper of Marco Di Francesco on this. Correct me if I'm wrong.
Yeah, thank you for the comment. Let's discuss later, and we'll look into it.
So it's good to read sometimes math biology papers too. Any other comment? So thank you very much.